Firearms are some of the most precisely engineered mechanical devices in the world. Machines built to withstand extreme pressure, cycle with flawless reliability, and operate safely under punishing conditions. Yet few people ever see inside a modern gun plant, where steel billets, aluminum forgings, polymer granules, and precision-machined components come together under strict quality control. Behind every finished firearm is a factory ecosystem featuring CNC machining centers, automated forging lines, heat treatment furnaces, broaching machines, polymer injection presses, robotic measurement systems, and ballistic testing ranges. And today on the How Factory, we're going inside those facilities to see how firearms are manufactured at scale. From raw metal to fully assembled, rigorously tested products designed for decades of use. What looks like a simple tool in the hand is actually the result of thousands of machining operations, computer-guided measurements, and metallurgy techniques perfected over generations. The journey begins with raw materials. Firearm manufacturers order steel and aluminum in the form of billets, bars, or forgings. Critical parts, like barrels, slides, bolts, and frames, require alloys engineered for strength, corrosion resistance, and heat tolerance. Aluminum receivers start as forged blocks compressed under massive hydraulic presses. Steel components begin as bars or partially formed shapes, created in high-temperature furnaces and hammer forges. These heavy-duty forging operations align the metal's grain structure, making parts far stronger than if they were cut from raw stock. Each piece is inspected for cracks, voids, or imperfections, using ultrasonic scanners or magnetic particle testing. Only perfectly clean forgings move forward. From here, the heart of firearm manufacturing takes over: CNC machining. Multi-axis machining centers, some with robotic loading arms, clamp each forging or billet and carve it down with precision tools. Over hours or even days, cutters remove material to reveal highly detailed internal and external geometry. Slides receive precisely machined rails and surfaces. Frames are drilled, milled, and tapped for various components. Bolt carriers and locking parts are shaped to extremely tight tolerances, because alignment and timing between components determine a firearm's reliability and safety. Throughout machining, quality control probes measure surfaces at micron-level precision. If a tool wears or a cut drifts outside tolerance, the machine automatically compensates or pauses the operation. Barrel production is one of the most specialized processes in the plant. It begins with a cylindrical steel blank drilled, using deep-hole boring machines that slowly push long drill rods through the metal while flooding it with coolant. After drilling, a reamer enlarges and smooths the bore to a controlled diameter. Next comes rifling, the formation of spiral grooves that stabilize a bullet in flight. Factories use several non-instructional industrial methods. Broach rifling, where a long-toothed rod pulls grooves into the barrel. Button rifling, where a hard metal button is pushed or pulled through to form grooves by cold working. And hammer forging, where external hammers compress the barrel blank around an internal mandrel carrying the rifling pattern. Each method requires massive machines, hardened tooling, and exact metallurgy. After rifling, barrels are stress-relieved in heat treatment furnaces to stabilize the steel. Once machining is complete, nearly every critical metal component undergoes heat treatment. Furnaces precisely cycle parts through heating, quenching, and tempering stages to increase hardness and fatigue resistance. Parts like bolts, locking lugs, and sear components endure extreme stress during operation, so metallurgical consistency is critical for long-term durability. Heat treat ovens use inert atmospheres to prevent oxidation, and computer systems log temperatures and soak times for every batch. After heat treatment, parts are shot peened with steel or ceramic beads to improve fatigue strength and surface integrity. Surface finishing is another essential step. Depending on the model, components may receive bluing, parkerizing, anodizing, nitriding, Cerakote, or other finishes to enhance corrosion resistance and appearance. Before any finish is applied, parts pass through multi-stage cleaning lines, ultrasonic baths, degreasers, abrasive blasting cabinets, or vibratory tumblers. Robots apply coatings with uniform thickness, and curing ovens harden finishes to withstand years of wear. While metal parts are being machined, the polymer department produces grips, stocks, and polymer frames using injection molding machines. Polymer pellets are melted and injected into steel molds under high pressure. These molds form complex shapes complete with internal reinforcements, textured surfaces, and mounting points. After cooling, parts are ejected and automatically trimmed. Some polymer frames incorporate metal inserts that are molded in place, combining strength with weight reduction. Each molded piece undergoes dimensional inspection before moving to assembly. As components across the factory reach completion, they enter sub-assembly stations. Triggers, safeties, magazine catches, extractors, and other small mechanical parts are assembled using jigs that ensure alignment. Springs are inserted with automated feeders. Pins are pressed into place using pneumatic or hydraulic presses. Technicians follow strict documentation and testing protocols because these small parts play critical roles in timing and function. Sub-assemblies are inspected for spring tension, free movement, and surface finish. Next comes full assembly, the stage where the firearm actually takes shape. On a long assembly line or in modular work cells, technicians marry the major components: frame or receiver, slide or bolt, barrel, trigger assembly, magazine interface, and control levers. Workers follow standardized build procedures, and torque tools ensure screws or fasteners meet specification. Throughout assembly, gauges check clearances, travel distances, and mechanical engagement of safety systems. A single firearm may undergo dozens of checks before it even leaves the assembly bench. After assembly, firearms enter the testing stage. Every unit undergoes mechanical checks for cycling, dry function inspection, and measurement of critical safety mechanisms. Only after passing internal tests do they move to the ballistic test range. Here, each firearm is secured in a test fixture, not operated by hand, and fired remotely using proof loads that generate pressures far above normal. This extreme test validates barrel integrity, chamber strength, and safe function under stress. Technicians analyze spent cases, bolt face imprints, ejection patterns, and internal wear marks. If the firearm performs normally, it passes proof testing. Additional function testing follows using standard ammunition to confirm cycling reliability. Firearms that fail are sent back for diagnosis and rework. Once testing is complete, each firearm is cleaned, lubricated, and reassembled for final inspection. Serial numbers, model details, and compliance markings are engraved or laser etched. Quality inspectors check cosmetic finish, alignment, trigger feel, safety function, magazine fit, and general build quality. Only units meeting every requirement move on to packaging. Packaging is its own controlled process. Firearms are placed into custom-cut foam inserts or molded cases along with manuals, locks, and accessories required by regulation. Cases then travel to labeling stations where identification codes, barcodes, and shipping labels are applied. Warehouse automation sorts packaged firearms onto pallets bound for distributors, military customers, law enforcement agencies, sporting goods retailers, and international markets according to local laws. Behind all of this is an enormous documentation and compliance infrastructure. Modern gun plants track every component through serial-numbered batch systems and digital manufacturing records. Metallurgy data, torque logs, heat treat profiles, test results, and assembly steps are recorded to ensure traceability and safety compliance. Inspection labs perform metallographic analysis, hardness testing, dimensional metrology, and fatigue simulation. Factories must maintain strict security, controlled access, and regulatory oversight throughout the entire process. What makes firearm manufacturing remarkable is the combination of brute force industrial machinery and microscopic precision. A slide or bolt may endure explosive pressure, yet its surfaces must be polished to near mirror finish for reliable cycling. Barrels face thousands of high-temperature pressure pulses, yet their rifling geometry must remain perfectly uniform. Safety mechanisms must function flawlessly every time under every condition. These machines may appear rugged and simple from the outside, but their internal engineering is refined, exact, and deeply complex. And that is exactly how modern firearms are forged, machined, heat-treated, finished, assembled, tested, and certified. A blend of metallurgy, precision engineering, robotics, and strict quality control working together to produce some of the most precisely built mechanical systems on Earth. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines and systems behind everyday products.